Okay, let's start. Good morning. So today we're going to keep working on differential calculus. I want to give a couple definitions, and then we're going to spend most of today and probably tomorrow too handling certain specific examples as to how to compute at least the first derivative of a function. So we're slightly behind schedule, even with this adjustment, but I think it's going to be good. And if needed, we'll just concatenate our time, or the time reserved for differential forms into 4 weeks, perhaps. Do something like this. Before I start, I want to ask you, how many of you studied the proof of Taylor approximation in 3210? Kind of. Yeah, so, yeah.
Oh, I think we sort of touched on it. But
Did you prove it?
I'm not 100% sure.
Okay.
We talked about it a lot. I think we might have proved it. I was in your class.
So yes.
If you proved it, then we proved it.
Yeah, we did.
I don't have my notes from that class, so I don't 100% remember.
Yeah. So for those of you who haven't taken 3210 from me, I actually defined, the presentation I gave for the first derivative to begin with was sort of, oh, this is the first order Taylor approximation to begin with, at the very least, with this little o notation. That's sort of like the idea. Up to first order, my function is this simpler function. And yeah, so in the textbook, you first study sort of real analytic functions. These are functions that have converging power series expansions at all points. And then you sort of specialize to the case of Taylor approximation. You say, oh, even if your function is not real analytic, it might be the case that, let's say, if it is 5 times differentiable, you should be able to expand the Taylor, the virtual, so to speak, virtual Taylor series up to 5th order. And there's certain theorems and stuff like that. I was able to discuss this in the final week. And even then, I was reviewing my own lectures. And I'm saying it's like next time I teach this class, I'm going to prove the Taylor approximation much earlier. So I would highly recommend that you at least have a look at that video, so the week 14 video for 3210 on my channel. Because somehow, really, Taylor approximation is sort of the main thing, or one of the main things you should get from this class. Is like, norm spaces, metric spaces, continuity. These are not really the main concern of calculus. The main concern of calculus is to be able to approximate things. You need to be able to say things like, oh, up to first order, this complicated thing is this, or up to 5th order, whatever is needed, depending on the situation. So Taylor approximation is really one of the fundamental ideas of calculus in single variable and in multivariable. Okay, and so we're getting close to it slowly. Okay, that's all I wanted to say. So here are some more definitions and some more symbols and stuff. As usual, our standing assumption is that M is an open subset in some norm space E, and N is an open subset in a norm space F. And as usual, I'm going to have functions going from M to N. We define what it means for a function that goes from M to N to be differentiable, to be continuously differentiable, so C1. We came up with the derivative and so on. And we had defined these directional derivatives. And so in this specific case of E, the space of n tuples, okay, we have this specialized notation, which is the partial derivative notation. So d by dx1 of f at the point x is nothing but the directional derivative of f at x along the first standard basis vector, so 1, 0, 0, 0. Okay, assuming that these exist, of course. And likewise, the second partial is directional derivative along the second standard basis vector, and so on. Okay? Now, I should also mention the standard identification we have between tuples of numbers and matrices is that a tuple, right? So these are n different and possibly different numbers that are separated by commas. Under our standard understanding, this turns into an n by 1 column matrix. Okay? So this is not the same thing as a row matrix. This is a column matrix. Because we would like to imagine that matrix multiplication, or applying a linear transformation to a vector, corresponds to left multiplication. Okay? We could have done it the other way around. We chose it because that's sort of how we learned us, at least in 2270, for instance. But that's something you should always keep in mind. So under the standard identification, this is going to be x1, x2, dot, 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 xn. And not the transpose of it. Okay? The row matrix will be the transpose of this. This is a standard identification between the tuple notation and the matrix notation. Okay. Now, here's an exercise. More generally, really, instead of saying E is R multiplied by itself n times under this Cartesian product, you can just take n norm spaces and just take E to be the product norm space. And again, there is defined the partial derivatives. So this derivative is essentially the one that you obtain by fixing the components coming from these parts and taking the derivative along this direction. I'm going to leave it to you as an exercise to define it. It's not very important for us, at least for now. But you should think of it like this. If these ultimately allow you to think of the derivative as the matrix of partials, which I'm going to write over here, this formalism allows you to think of block matrices. So matrices whose entries are matrices themselves. This is sometimes an important thing to be able to do. So the heuristic is this. If E is Rn and F is Rm, okay, so I have these, and F is a function from m to n, okay. So an x, a point in M, is going to be an n tuple. Its output, f of x, is going to be an m tuple. So the n and m sort of are opposite somehow. It's inconvenient. But f of x is going to be f1 of x, f2 of x, dot, 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 f sub m of x. That's going to be a point in n. It's going to be an m tuple. Okay. Now, based on our definition, if the derivative of f at a point exists, it should be a linear transformation from Rn to Rm, which means that it should be an m by n matrix. And its components, its entries, are going to be, well, basically all the partials of all of these components. And the way I imagine it is that under this identification, each row of this derivative matrix should correspond to one of the components. And as you change the different partials, you should be switching over to different columns. That is to say, this should look like this. So in the first row, I'm fixing f1, and I'm running over all different partials. X, n. Then here, in the first column, the component function is going to change, but the partial is going to stay the same. So ultimately, you're going to end up with the final function, final component. Okay. Give me this matrix. And so ultimately, what do we have here? We have m rows, m components correspond to m rows, n partials correspond to n columns. It's going to be an m by n. In a different presentation, this is how you would define the derivative. But somehow it is more cumbersome to write down. I feel like this is not easier to think about. And it's much more restricted. And some of the examples I'm going to do today, I hope, is going to justify that as well. Now, at this point, let's just leave it as a heuristic. We're going to really show that indeed, if the derivative at x exists, it has to be this matrix under the standard bases and blah, blah, blah. But we're not going to prove it yet. Okay. Any questions about this? So sometimes you would see the phrase Jacobian matrix, or the total derivative, or the Frechet derivative. This has like 5 billion names. I think it's just easy to call it the derivative. That's the natural definition. Again, examples I'm going to give later today and probably tomorrow too, hopefully justify this reasoning in the definition. Comments, questions? Okay. So how do you define twice differentiability? Well, the benefit of defining differentiability the way we did is that you can iteratively define higher order derivatives like so. Well, if f is C1, that is to say, f prime of x exists for each x in M, and furthermore, the mapping that takes x to f prime of x, that goes from M to the space of bounded linear operators, is continuous. So that's C1. Well, all I'm going to ask is f prime itself is a C1 function from M to the space of bounded linear operators from E to F. Now, does this work? Does this even make sense? Well, we talked about how, for any two norm spaces, the space of bounded linear operators from E to F itself is a norm space under operator norm. And this, again, is a metric space. And so I can ask, oh, can I differentiate this? OK? So this makes perfect sense. Now, the problem is that this is not very easy to handle, because when you write this out explicitly, this means this, i.e., for any x in M, there's a unique, well, the derivative of this should be f prime prime of x. Maybe I should write it like this, f prime of prime. And it should go from here to something, right? Bounded linear E, bounded linear E, F. Now, the downside is that now this expression is nasty. OK? So we're going to bite the bullet. There's two ways of defining or thinking about higher derivatives. Either you're going to worry about second order partials. So even in this case, for instance, I have m components, n partials, which means that I'm going to have n squared second partials. Some of them are going to match, hopefully, but m times n squared partials. Either you're going to have to think about m times n squared things, or you're going to have to think about one thing that takes values in a bizarre space. So somehow, for now, in the problem set due this Friday, for now I want you to use this formalism. Probably on Wednesday we're going to figure out how to manage these spaces. Okay? But technically, in terms of definitions, you can just keep iterating this idea and define what it means for a function to be ck. Okay? F is ck if it is ck minus 1. So k times continuously differentiable. If it is k minus 1 times continuously differentiable, and the k minus first derivative is continuously differentiable. And again, it's taking, you can imagine, values in some very complicated space, at least for now. And f to the k minus 1, so this is the k minus first derivative. You see, this is how you get rid of writing these things. You just say, oh, this is the regularity, without saying what is the input space and output space. This is something people do all the time. And of course, let's also define C infinity, infinitely many times differentiable. Oh, this is nothing but functions that are ck for any k. Okay. So these are just definitions for now. We're not going to go any further. Now I want to switch over to specific examples. Okay. Any questions before I continue? Okay. Now, I had given last Friday, I mentioned an example of a function that depends on two numbers. Okay. So it is within the realm of Calc 3, if you want, such that at 0, at the origin, all of its directional derivatives exist. But I told you that somehow its derivative doesn't exist. And that's why I first define f prime of x instead of directional derivative or partial derivative. Now, this class is not supposed to be a class where we do explicit calculations, but at least until further notice, it would be good for you to take a piece of paper and try to follow the calculations and keep me honest. Okay? Example. Now I'm going to look at f goes from R2 to R. Okay. Takes xy to the following. X cubed divided by x squared plus y squared if this is well defined. That is to say, if xy is not 0 and 0 otherwise at 0, that is to say. Okay. First of all, the point of contention, of course, is the origin. So I'm fixing the base point to be the origin. First of all, before even asking about differentiability, you should ask about continuity, because we know that differentiability is going to imply continuity. So if a function is not continuous, then certainly it's not differentiable. Is it continuous? Is this function continuous at 0? So that is to say, if xy converges to 0, does this expression converge to 0? Yes, right? Because the numerator is of higher order than the denominator. It's going to decay faster. It's going to go to 0. So it is continuous at 0. In fact, it is continuous everywhere. And if I wanted, I could have written f is in C0. OK. Let's now look at directional derivatives. So f is continuous everywhere. Directional derivatives. At the origin, at 0, 0. How do I compute the directional derivatives? Well, I need to take a certain limit. Let's recall the definition. So if I were to take a v, let's say, because for a directional derivative, not only do I need to fix a position, but I also need to fix a direction, a velocity. And so let's call it pq. Now, what is the definition of the directional derivative of f at 0, if it exists? So, okay. Now, in terms of the types, this should be something in the output space. Okay, so this is going to be a number. It's going to be a scalar, because the function takes values in the reals. I'm always, before computing anything, I'm always keeping track of the dimensionality. Okay, the dimensions have to match. Okay, this is going to be a number. And what is this defined, if at all? Well, I'm going to do the following, right? This is my base point. And then I'm going to approach it using scalar multiples of this fixed vector. T, or maybe let's say H, PQ, minus f of 0, 0. This is a number, but of course I need to divide everything by h and then take h to 0. This is the definition of the directional derivative. Okay? So let's figure out what this ratio is. This drops out because f of 0, 0 is 0 by definition. Now what is this? This is nothing but f of xp, f of hp, comma hq. Divided by h. Okay? Now, I know the formula for this. Again, let's remind ourselves, when we write this, we're implicitly assuming that h is not 0 itself. Okay? H is something that approaches to 0, but not exactly 0, but because otherwise this doesn't make sense. Okay? So we have two things to do. Let's first assume that PQ itself is not 0. Okay? If it is 0, then this is going to turn out 0 no matter what. Technically, it is still well defined, actually. But let's assume that V is not the zero vector. Okay? In that case, that means that the input of f is not the 0 vector, which means that in the piecewise definition, I need to be using this formula. Okay, so plugging in, I get this. So x equals hp. Okay, hp cubed divided by nh times hp squared plus hq squared. Okay, now I can do some rearrangement. Of course, P and Q here are constants, right? They are fixed. I fixed the direction, and H is the variable of the limits. But you see, this becomes this. And then I have H cubed times P cubed divided by, well, I have a factor of H squared here. and another factor of h squared, so I can take it out. H cubed, I have an additional h, times p squared plus q squared. Are you happy so far? H is not 0, right? So that I can cancel these out. But then I'm doing nothing but taking the limit of a constant expression. This expression now is constant in h, which means that the limit has to be that expression. Is this a number? It is a number, right? P is a number, p cubed is a number, denominator is a number as well, so this is a number. So the type matches, and you see this is the directional derivative. V is arbitrary, but fixed, and at each direction, the directional derivative of f at 0 exists, and it is precisely this expression. Somehow, of course, it's the function itself. And this is no coincidence, but let's not talk about why it's not a coincidence. Okay, so let me write it. Thus, in more abbreviated notation, this is nothing but p, what was it, p cubed, divided by p squared plus q squared for v equals pq, not equal to 0. And I'll leave it to you to verify that at 0, the directional derivative along 0 itself is going to be 0. That's an exercise. That's by definition, essentially. Are we happy so far? Okay. Now, I claim that this function, even though all directional derivatives at the origin exists, is not differentiable at the origin. By the way, so if all directional derivatives exist, certain partials exist too, right? So we can just plug in v equals 1, 0. To get the x partial. In this expression, p now is 1, q is 0, so this is just 1. Y partial. Now p is 0, q is 1, so the y partial is 0. Okay. Is it differentiable? Well, I'm going back to this idea of starting at the origin, perturbing it just a little bit, and trying to get linear response. Right? That's how we did it. So let's say hk in R2. Again, this is not the 0 vector, but you should think of it as a very small vector. Right? This is an infinitesimal in a sense. And so I look at this. I start with the origin, and then I perturb it just a little bit. And I'm saying, can I write this as f of 0, 0 plus some linear function of this guy plus higher order terms, if possible? Well, what is this? This is nothing but hk. Okay. And hk, I'm assuming, is not the 0, 0 vector, which means that I need to be using this formula again. H cubed divided by h squared plus k squared. Okay. Now, f of 0, 0 is 0 itself, so that's not a problem. But I need a first order term. Okay. So I need something like this. This is 0. I need something like this applied to hk. And because of the type, right? Because f goes from R2 to R, its derivative 2 should go from R2 to R, which means that it should be a 1 by 2 matrix, which makes sense. Because the only way this can come out as a number is if this is a 2 by 1 matrix. Okay? So this is a dot product in a sense. Little o of hk. And this is 0. You ask, can I put this in this form for some numbers, let's say a and b? Okay, so this is going to be of the form a, b, and so this is going to turn into a, h plus bk plus higher order terms. And well, you can't. Maybe that sort of requires some argument, but I think for this class we can just assume that you can immediately see this, or you can immediately say this at the very least. That is to say, there is no a and b such that for whatever function that decays faster than the norm of hk, we can get this function. Okay. This has no linear part whatsoever. Okay. So this doesn't work. You don't get to approximate up to first order. Okay. So the flavor is very different, you see. When we're doing the directional derivative, we're just taking a certain limit. It's a calculation. When it comes to actual derivative, it's about whether or not you can fit into a formula, into an approximation. Any questions about this? So as the math gets more and more complicated, the nature of the calculation likewise changes. Okay? Comments, questions? This is a very important point. So don't be fooled by this idea that, oh, you get to compute the partials, and you look at the row matrix 1, 0, and that's a derivative, you see? Even though all of the components exists for the supposed derivative, if you were to put them in a matrix, it doesn't fit into the approximation. And that's what makes or breaks differentiability. Now, you could say, OK, so what's your problem? OK, maybe the derivative doesn't exist. But at the very least, directional derivatives exist. And they exist in any direction. So I can just do one-dimensional approximations. And that is true. You can. Directional derivatives existing is still some sort of smoothness. But I guess the best way to convince you that still this is the better way of thinking about differentiability is to ask you to plot this function on a 3D calculator. Plot this function, and Desmos 3D can do this. And the moment you see the graph of this function, you're going to say to yourself, oh, this function is not differentiable at the origin. It's not going to fit to your intuition of differentiability. There's something bizarre going on, and you're going to want to say that this function is not differentiable, probably. And somehow, even though it's not perhaps very clear how, this definition of, oh, I get to approximate the function up to first order, captures your intuitive idea of differentiability, but not the directional derivatives. Okay, so I'm going to leave it to you to plot this. If your function takes 2 inputs and spits out 1 output, you get to still plot it, and you can still think about it intuitively, but somehow, clearly, it's like there's nothing stopping us from going to higher dimensions, infinite dimensions, whatever. And this formalism still applies pretty much verbatim. That's why I defined it in more generality. Okay. Now, all hope is not lost, and there are certain situations where just computing partials end up being sufficient, and we're going to see why or how, under which circumstances. But we'll get there. We'll get there later. Okay. I just want to keep calculating more things today. Any questions before I continue? Okay. Another example. Probably I'm going to take tomorrow too for calculations. Ultimately, what I would like to do is to compute x squared for x, a square matrix, the derivative of x squared. I mentioned this to some of your colleagues. And I should also mention on Canvas, I uploaded a set of lecture notes about calculus using matrices, because it turns out that this is very important for machine learning and other things. But that's for engineers, OK? So they do sort of derivative of this and that left and right, but there are gaps as usual. So OK, what's the next example? Oh, OK. Here's a nice example. It's an exercise, actually. There's a very similar exercise. Where should I write it? I'm going to write it over there. Yeah. Because you could say, oh, in this example, the problem was that, well, the directional derivative d sub v of f at 0 wasn't a linear function of v. Right? It was a nonlinear function. Even though, even if the directional derivative is a linear function of the vector, it might end up being the case that f is not differentiable at that point. So this exercise is about that. This is very similar. X cubed y, x sixth plus y squared. Again, this formula applies for x, y non-zero. If you're at the origin, you put 0. And again, numerator doesn't decay faster, actually, but it decays just enough, let's say. And so this is still continuous. That's not a problem. So v sent to the directional derivative of f at the origin. This is a linear function. In particular, directional derivatives at all points at each directions exist. But again, f prime doesn't exist. Okay? Calculation is very similar. I'm going to leave it to you. Here's the next example I want to do. Product rule. Let's say, of course you know this, but the point of this example is going to be that you can use multivariable calculus to derive formulas that you already know. Let's take two functions that are differentiable. These are real valued, single variable functions. We know that the product of them too is differentiable. And we have a certain product rule, or the Leibniz rule. Right? Okay? This you should probably be familiar with. You saw this in calc. You probably proved this in 3210. First, let's practice this little o notation. Okay? So what I'm going to do now is not going to be related to multivariable. I just want to exemplify again how useful this little o notation is. Okay. So the point is, I'm going to try to approximate this up to first order. OK, so what is this? This times this. But I know that phi and psi are differentiable, so I can approximate both of them separately. That's the approximation for this guy. And the approximation for this guy is like this. OK, now we expand everything. The point is that when you're expanding this, if you're multiplying anything by little o, that's going to still stay as little o, so you can just absorb it into little o. And if you multiply h by itself, that's going to be h squared. That's also little o. H squared decays faster than h does. So all I need to do is to look at the first parts, basically. This by this, plus this by this. Plus this by this. And then what else? This by this is O. This by this is O. This by this is O. O, O. Everything else is O. Everything else is a higher order term. There you go. Didn't use any epsilons, any deltas. I just did algebra. You see, this is the power of Taylor approximation. You take a complicated function, differentiable, and you get to pretend that it's a polynomial. OK? There you go. Any questions about this? Of course, what is happening underneath, this little o is managing all those limits and epsilons and deltas. Does it for you. But you have to be careful. Those of you who have taken 3210 from me have sort of suffered through how to use this little o. So it can be somewhat problematic sometimes. But if you're careful, it works just fine. Another thing, too, is that part of this class is supposed to be literacy, and this is commonly used. So you're going to see these kinds of things if you end up reading more advanced stuff. OK, so this was an example for the little o notation and how to use this first order approximation. Now I want to sort of change my perspective and somehow derive the same formula using multivariable calculus. Now, one way to do this is to figure out how to think of phi times psi as a composition of possibly multivariable functions. Well, one thing you can do is the following. This is the product function But you could say, oh, this function is really the composition of, well, one function that goes from reals to r squared, and another function that goes from r squared to r, where this is just multiplication of the two entries, and this is the function whose components are phi and psi. So let's say, yeah, so let's denote it like this. So this function, phi comma psi, is a function that takes x to phi of x comma psi of x. And this function, let's call it maybe mu multiplication. Okay? Let's say r comma s goes to rs. Okay? And so phi times psi is nothing but this composed with this. Are we happy so far? Now, it's more complicated looking, but sometimes splitting or factorizing your procedures into possibly simpler components ends up becoming very useful. Probably I'm not going to be able to finish this, but the point is this. Insofar as mu multiplication is differentiable, and this function whose components are these two functions this function is differentiable, then the derivative of this should be, by way of the chain rule, related to the derivatives of these. If these two are differentiable by the chain rule, what should be the case? The derivative of this, let me write it over there actually, here. Okay, what is the derivative? Derivative of the outer one evaluated at this point times the derivative of the inner one. Okay, so we're going to spend more time on this because I'm running out of time. I want to take my time in doing this. So tomorrow we're going to keep working on this example, and then we're going to look at dx squared by dx, where x is a square matrix. What is the derivative of x squared? Okay, thank you. I'll see you tomorrow. Okay, let's start. Good morning. So today we're going to keep working on these examples. Yesterday we were discussing the product rule, and I wasn't done. I sort of verified it using this little o notation by just expanding the product up to first order. But I told you that we can use also multivariable calculus and chain rule too to derive this product rule, which we're going to do. And then I want to compute the derivative of x squared, where x is a square matrix. But before that, I want to say a couple more things. First of all, I had given this function as an exercise yesterday. So this is a function that is supposed to have all directional derivatives at the origin. I told you that this was continuous, but it is not continuous. In particular, it's not differentiable. Still, directional derivatives exist. So you see, that's another perhaps reason. It's also nice, perhaps, let me mention this as well. Here's an example. Even if you have a function that is continuous at the point, and even if all of its directional derivatives exist at that point, still that is not sufficient for differentiability. Okay? This, and function is defined like so. This is x if y is x squared, 0 otherwise. Then this function is continuous at the origin. All of its directional derivatives exist, but this is not differentiable. Directional derivatives at the origin exist, but f is not differentiable. So f prime of 0, 0 doesn't exist. So somehow directional derivatives, they're not nice enough things. And I think I mentioned the C1 metric. I had defined this, but likewise you can define the CK metric. All you need to do is to look at the higher order derivatives. And just like you looked at this unboundedness or boundedness of the differentiation operator in problem set 2, you sort of can sort of put them together to get a metric that incorporates the kth order, all information up to kth order. Just you define it just like you define in C1 case. Not going to spend time on that. What I do want to mention is this. First of all, well, maybe before the theorem. Yesterday I mentioned this as a heuristic, but let's try to clarify this a little bit. So observation, if, as usual, I have two open sets in norm spaces, M and N, and I have a function from M to N, is differentiable. So if f prime of 0, f prime of x exists at x. And let's also say that E and F are spaces of tuples. We said yesterday that the derivative of f at x is supposed to be an m by n matrix. And I told you the indices are supposed to be the partials of all the components. How can we get this? So then is an m by n matrix. This much is essentially by definition. This is by the identification of the space of m by n matrices and the space of linear transformations from Rn to Rm. So by the isomorphism, once I have the fact that I can think of f prime of x as an m by n matrix, how do I index into the specific entries and realize that they're supposed to be the partials of the components of f? Well, I'm going to use this idea that directional derivatives, on the one hand, are related to partial derivatives, and on the other hand, related to the derivative. If this exists, remember, we have this. The directional derivative of f at x in the direction of v, insofar as this derivative exists, is the same thing as f prime of x applied to v. So this is what I'm going to use. Because I know, by definition, for instance, the first partial, right, so let's say beta 1 is the first standard basis vector, then the directional derivative of f in this direction is nothing but the x1 partial, right? So I guess I should write it like this, x1. This partial is the directional derivative of f in this direction at x. But then by this formula, this is nothing but f prime of x applied to beta 1. So this is a tuple. This is nothing but f prime of x applied to beta 1, which is the same thing as this matrix multiplied by this. Well, what is the effect of taking a matrix, an m by n matrix, and multiplying it by one of these standard basis vectors or matrices? Well, this corresponds to singling out the first column. Right? When you multiply this, this is going to pick out the first column. So the first column of f prime of x has to be this. You see? So this is first column of the matrix f prime of x. And so you see, in the matrix f prime of x, in the first column, you're fixing the first partial. And what are the different entries? Well, different entries correspond to the different components of f. Because f goes ultimately from some subset of Rn to some subset of Rm. So f has m components. For each component, you're going to have one entry in the column. And likewise, if I were to feed into this the second standard basis, that would correspond to the second partial, second directional derivative, f prime of x applied to the 0, 1, 0, 0 matrix, which would correspond to the second column of f prime. Does this make sense? So this is how you would index into f prime of x. By feeding it nice column matrices. Now the theorem is that we would like to be able to revert this procedure. We would like to be able to say, under certain circumstances, insofar as, let's say, the first partials exist, f prime should exist also. This is true under the condition that for all first partials exist and they are continuous. So I'm not going to prove this theorem now, but I'm going to use it today for the purposes of calculation. The proof of this requires mean value theorem, which we're going to prove probably tomorrow, and then we'll be on our way. Okay, so we're going to prove this later. So let me write it like this. Well, first, let's say it like this. Suppose E is Rn and F is Rm. Then F is in C1 between these two subspaces. or subsets. In fact, let me write it like this. To be more explicit, and let f of x, well, let me write it like this. And so explicitly written, this would look like so. F takes values in Rm. It has m components. Each input x has n components. OK. Then f is in C1. If and only if each partial of each component exists and is continuous. For any ij, the ith partial of the jth component exists. And is a continuous function from m to, well, when you think about it, it takes values in reals. Okay. Similarly, f is in ck, k times continuously differentiable, if and only if all kth order partials, including mixed partials, exist and are continuous for each component. Now, writing it explicitly like this becomes more cumbersome because we didn't develop the necessary sort of notation for this. So I'm just going to write it like so. F is in ck if and only if all mixed partials, possibly mixed, all partials, let's say, of all components of f of order k exist and are continuous. Okay, so for C2, I would need the second partial relative to x1, and then x1 partial, x2 partial, x1 partial, x3 partial, x1 partial, xn partial. Then I would need x2 partial squared, x2 partial, x3, x3 partial, x2 partial, x4 partial, and so on, all of them. So I have in total n squared partials for each component. Some of them are going to match, of course, because ultimately the order of partials should not matter. We're going to prove that as well. But that's that. Okay. Any questions about this statement? So we're going to prove this later. OK, let's go back and keep working on our examples. We were working on the standard product rule for single variable functions, but we were trying to recover it using multivariable. And what was the setup? I have two functions, let's say phi and psi, from reals to itself, differentiable. Then their product too is differentiable. And indeed, the derivative has a specific formula. Derivative of the first one times the second plus the first one times the derivative of the second. Right. OK, so we were trying to recover this using multivariable. And what I told you was, well, I'm going to think of this. I'm going to try to think of this as a composition of two functions. First function is the function that takes one input, one scalar, and gives me back two numbers. So it's a function from reals to r squared, whose components are phi and psi. And so this is this function. Okay, it goes from r to r squared. First component is phi, second component is psi. And then the second function is going to be multiplication of numbers, which I denote by mu. And so this product function is the same thing as this composed with this. So let me write it perhaps explicitly. X goes to phi of x, comma, psi of x. This is the first function. And mu is, it takes two numbers, r and s, let's say, and gives you back r times x, s, multiplication. OK, so that this product function is multiplication composed with this component function. Are we happy so far? I just factorized this product function into two more complicated looking functions. OK? Then, assuming that both of these components are differentiable, to compute the derivative of this, I can just use the chain rule and just multiply the derivative of this with the derivative of this. For that, I need to have beforehand that this is differentiable and this is differentiable, OK? You cannot just apply chain rule to things that you don't know is differentiable. And that's going to be something that you're going to have to deal with when you're trying to differentiate, I think, the last problem in the upcoming problem set, which I think I'm going to extend the deadline for. But we'll see. Assuming both mu and phi psi are differentiable, by the chain rule we have that the derivative of this is the derivative of this guy evaluated at the output of this times the derivative of this evaluated at the input. And so OK, let's count the dimensions. this first function, okay, the inner function, goes from r to r squared. Its derivative, evaluated at a point, insofar as it exists, has to be, again, a linear transformation from here to there, which means that in terms of matrix notation, it should be a 2 by 1 matrix. Okay, this is the dimension count. Okay. So this is going to be a 2 by 1 matrix. So it's going to be a row matrix. Similarly, mu goes from r squared to r insofar as this derivative exists. Again, it has to be a linear transformation from here to there, which means that it should be a 1 by 2 matrix. Okay. So you see, it does make sense writing it like this. 1, 2, 2, 1. And when you multiply, you're going to end up with a 1 by 1 matrix. That is to say, a number. Okay? This is what we want, because ultimately, this is a scalar. Okay? Whatever this is should come out as a 1 by 1 matrix in terms of matrix algebra. Are we happy with this so far? I haven't even thought about computing these yet. Okay? I'm just looking at dimensionality. Does it make sense? Okay? In a sense, I'm sort of allocating memory, okay, in terms of computer science. Now the problem is, first of all, do these exist? And so on. So we're going to have to compute those. Now you can compute the derivatives, and these derivatives do exist. You can compute these derivatives using this, first order approximation or expansion that I've been using. Let's just use a theorem. Okay, it's much more convenient, especially for sort of nice functions like this. So multiplication, you should think, is a very nice function. Okay, nothing should go bad with multiplication. So what is this, for instance? Well, what can it be other than the 2 by 1 matrix, where the first coefficient is the derivative of this, and the second coefficient is the derivative of this? Okay. Using the theorem. Maybe I should say C1 actually, so that we can use the theorem. It doesn't matter, of course. And then what is the derivative of mu at a typical point, Rs? Right? So now this is going to be a 1 by 2 matrix. So I guess I should have written it the other way around, actually. So it should look like this. So now this is 2 by 1. Mu prime is going to be 1 by 2. So mu is r times s. And so I should put here r partial evaluated at rs, and then the second entry should be s partial. Okay? But of course, what is r partial of rs? It is s. S partial of rs is r. And so these are differentiable. And multiplying then gives you this. So first I have this, but I need to plug in the appropriate entries, okay? So this is a derivative at Rs. To get this, R is phi of x, and S is psi of x. And so here, this is going to be psi, this is going to be phi. And up top, I have these. So this is essentially a dot product, right? This by this plus this by this. Does this make sense? Of course, we already had this formula. That's not the issue. I just wanted to show you the power. And maybe if you're like me, even at this stage, you're kind of thinking about this product rule. Like it takes a while for you to recover this. When I was taking this class, I had to think about this product rule even then. So if you're like me, you can always write everything out, apply chain rule, because ultimately chain rule has to work, okay? And just to be clear, to apply this, I really need the derivative of mu and this component function. If I were less lazy, I would have computed them more explicitly. So I'm going to leave that to you. Okay. Any questions about this example? Another very nice example, of course, is to try to recover the quotient rule. There's also another formula like this for the ratio of two functions, right? It's more complicated, but you can still recover it using multivariable. I'm going to leave that to you. Exercise. The quotient rule. Derivatives. Do we remember what this quotient rule said? Whenever applicable, this ratio is this times this minus the other way around divided by denominator squared. So the point of this exercise is to repackage this, the ratio of two functions, as the composition of a couple of perhaps simpler looking functions, and then apply the chain rule to recover this formula again. Okay, so that's that. Any questions about these? Okay, so now the promised x squared example. Probably this is going to take the rest of this class. And tomorrow we'll go back to our regular proof, definition, and all that stuff, theorem. The point is that it's not very hard, really, once you figure out how to think about it. But I want to sort of compute the same thing in multiple ways to give you a sense. So let's let E to be the space of n by n matrices. This is an n squared dimensional real vector space. It's a norm space under operator norm. So this is perfectly valid. And I'm going to take M to be the same thing as well, because any set is open in itself. That's why I can take M to be equal to E if I want. And likewise, I can take N to be F. And likewise, in fact, N and F2 are going to be the same space. My function from M to N is going to be nothing but take X, a square matrix, send it to X squared. Okay? We would like to compute the derivative of f at an arbitrary matrix, arbitrary point, x. Okay? Okay. So maybe I should say, for any x in M, okay, I want this, if it exists. It should exist, of course. You should say to yourself immediately, even though this is a matrix thing, I'm taking the squares, like a polynomial type of thing. It should exist. Computing is a different matter, of course. And so, in terms of the types, what should f prime of x be? How would you write it? What is its type?
It's like a matrix whose entries are matrices.
Don't think of it as a matrix, OK? We'll do that in a second. But in terms of just, if you just follow the definition, it should be, first of all, a linear transformation. From which space to which space?
From n by n to the linear transformation of n by n to n by n?
Yes, I mean, if I were to fix x, this is going to be a linear transformation from the space of matrices to itself. So f prime of x should take as an input an n by n matrix, should give as an output an n by n matrix. That's just following the definition. Okay. Let me just write it explicitly. Okay. So how to compute this? Well, the first thing you can do is you can say, OK, all this business is too complicated. Let's just pretend that this is an n squared dimensional space. It's r to the n squared. So this is just, I'm just going to think of everything as column matrices. OK, method one. So this is what you would call flattening, by flattening, or vectorization. Now, it will be painful to try to do this in general, so let's just be modest. If n is 1, OK, 1 by 1 matrices are numbers. And so this is going from reals to reals. Take a number, send it to its squared. OK, we know the derivative of this. There's nothing to do here. Okay, this is a number. You multiply any number by this number, and that's the derivative. Nothing to do. OK, this is fine. Even when the moment you take n equals 2, things are going to get slightly complicated, but I'm going to do it explicitly. OK, n equals 2. First, we need to fix an x. So now everything's 2 by 2. OK, x is a 2 by 2 matrix. So fix x, which is x, y, z, t. It's a 2 by 2 matrix. Well, by vectorization, I'm going to pretend that this is nothing but the 4 by 1 matrix, x, y, z, t. Okay? And so, but when I'm switching from this notation to this notation, you see, in this notation, it's not very clear what f does, because you cannot just take this matrix and take its square. Okay, it's not that clear. Maybe you can, but I'm not very comfortable with that. So what you need to do is, you need to take this, take its square, to come up with another 2 by 2 matrix, and then vectorize, right? So we need to compute this. xyzt times xyzt. So this is, okay. Again, this is going to be a 2 by 2. Again, you would benefit the most if you're following the calculations with me. So let's compute this matrix. xy plus yt in this entry, and then here I have xz plus tz. And then in this entry I have zy plus t squared. And so in terms of vectors, f of x is nothing but the 4 by 4 matrix with entry, f of x is nothing but the 4 by 1 matrix with entries this, 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 and that. And then xy plus yt, and then xz plus tz, and then zy plus t squared. Are we happy so far? I'm just computing things, okay? And don't worry, the punchline is that there's a much easier way to do this, of course. But it requires that you use this more sophisticated formalism. So everything has a cost, you see. And this stuff is complicated. So either your formalism is going to be sophisticated and complicated, or your calculations are going to be complicated. OK? Nope. So to be explicit, let me call the function that takes this 4 tuple, yes, to this 4 tuple, f tilde. It's not quite f itself, but it's related. So vectorized version of f is then f tilde that goes from r to the 4 to r to the 4. And remember, we're still in n equals 2. This is not the general case. Defined by xyzt goes to this matrix. And this is where I'm going to make a mistake, probably. Most amount of mistakes I make is when I'm sort of transferring calculations. Then xz plus zt, and then zy plus t squared. OK? So again, let's just take it as a heuristic that this function is very nice. And so to compute f prime, well, I'm just going to pretend that f prime is the same thing as f. F prime is the same thing as, I'm just going to pretend that f is the same thing as f tilde. So I'm just going to pretend that f prime is the same thing as f tilde prime. So I'm just going to compute the derivative of this. And so this is very nice. So all I'm going to do is I'm going to compute the partials of this function. OK. At t is prime. Now this is a 4 by 4 matrix. I have 16 partials to compute. OK. What was the rule? What was the rule? You see, I'm doing this even though I can do it much faster. What was the rule? Let's remember. On each row, I'm going to need to have one component. So this row is about this. I'm going to take this function, compute all of its partials. X partial, Y partial, Z partial, T partial for this. Second row, I'm going to take this function, X, Y, Z, T partials. Third row, this function, X, Y, Z, T partials. OK? This is how you do it. So let's go to X. Y partial is Z, Z partial is Y, T partial is 0. Are we happy with this? You should be familiar with this idea. OK. Now you take this. X partial is Y. Y partial is X plus T. Z partial is 0. T partial is Y. OK. This Z 0 Z no, sorry, T X plus T. This is a Z partial. T partial is Z. OK. X partial is 0. Y partial is Z. Z partial is Y. T partial is 2T. Does this match with your calculations? OK. So this is the derivative. Well, OK, it's correct. But I mean, what's the point of computing the derivative? Of course, it's so that you can approximate. So how do you use this? How do you turn this into something that you can use in this expression? Right? Because that's the point of the derivative. You want a linear response for the small perturbation. How do you get this back? You can do it, of course. You need to sort of de-vectorize everything, recover an appropriate expression that you can plug in here, where H is a 2 by 2 matrix. But it's somewhat complicated. Okay? And of course, this is only dimension 2, n equals 2. If n equals 3, then your spaces are going to have 3 squared dimensions. Okay? So it's going to be a 9 by 9 matrix. So you're going to have to compute 81 partials. Okay? So this is not the way to go. Okay? I mean, for some reason, for some purposes, it is, of course. But part of the reason why we have developed so much machinery is so that we can handle this much more efficiently. Okay. So I'm going to do method 2 in the remaining 3 minutes. That's going to be more than enough, actually. And this is going to work for any n, because I'm going to start with what I want. Okay? So f prime of x should take as an input an n by n matrix, and should give as an output an n by n matrix also. So just like I did with other things, I'm just going to open this up. Okay. Now you distribute. One thing you should be careful here is that matrix multiplication is not commutative, right? The order matters. So this is not x squared plus 2xh, whatever. It's more complicated. So this by this, plus this by this, plus this by this, plus h squared. H squared is second order in the norm of h. So this is a higher order term. This is a zeroth order term. This is f of x, which means that the derivative should be this. The point is that this expression for fixed x is linear in h. It's a linear transformation. You feed to this expression an n by n matrix, gives you back an n by n matrix, and does so in a linear fashion. That's the derivative. That's the definition of the derivative. Okay. Now I'm going to leave it to you to verify that indeed this does correspond to this. Another benefit of this is that, in fact, we're not using anything about the fact that these spaces are spaces of linear transformations from Rn to Rn. In fact, for any norm space, if I were to take E to be the space of bounded linears of that space, squaring it would again have the same formula. So this is not a finite dimensional thing. Okay? So somehow, if we can do things efficiently with 2 by 2, we can pretty much do things efficiently in infinite dimensions, assuming that you're following the formalism that we developed. Okay? Thank you. We'll continue tomorrow. Okay, let's start. Good morning. So today, well, my original plan was to start talking about mean value theorem in this multivariable setting. But before that, I thought it would be a good idea to sort of take stock and talk a little bit about how our notation, our formalism matches with or differs from the notation in the textbook. There are things like gradient, differential, different types of derivative-like objects in multivariable calculus. I think today I'm going to be taking my time sort of discussing all of these. And even before that, yesterday we spent around 30 minutes, I think, just computing the derivative of x cent x squared, where x is a square matrix. At least in the case of 2 by 2 matrices, we had two methods. Method 1 was by way of vectorization, and method 2 was basically by using the definition, right? So we started with f of x plus h, where h is a small matrix, and then we sort of expanded it out. And then we realized that up to higher order terms, f of x plus h can be written as f of x plus some function of h that is linear. And then by definition, we said, then that function has to be the derivative. And so I want to connect, and I mentioned that these two methods coincide. And so I want to say a couple more words about how we can connect this. I'm not going to do this connection completely. I'm going to leave it to you as an exercise. And today I'm going to be taking attendance. Is it the case that last time I took attendance, some of you didn't sign? Maybe not. OK. That's sort of what I had thought. Maybe I was imagining. So make sure that you do sign it, OK? So first think about this. What was the formula that we came up with the first method, with the method of vectorization? The formula is more complicated, but with method 2, the formula is nothing but f prime of x at a small matrix H, right? That's how I'm interpreting this. Is nothing but xh plus hx. Okay, so I'm saying that this right-hand side is an expression that is linear in H. So if I were to take two small matrices, or infinitesimal matrices, add them up, and apply this expression, that would be a linear function. Okay, so for instance, so f prime of x, h plus k. I'm imagining h and k are both infinitesimal 2 by 2 matrices, right? These are vectors, small vectors. I'm just using the formula. Okay. I know that matrix multiplication distributes. I have this. And then once I have the addition of square matrices, each of these products is a square matrix, and I can rearrange additions. I cannot change the order of multiplication, but I can change the order of addition, right? That's the point. And so I can combine these two and these two. Okay. So that's what I mean when I say this expression is linear in H. And likewise, you can imagine if I were to scalar multiply this infinitesimal matrix, this too would scale by the same number. So that's what I mean when I say this is linear in H. It's painful to write it as a left multiplication by some matrix, but that's what method 1 does exactly. It flattens the whole situation, writes everything as a column matrix, and then computes the partials and so on. Okay? Are we happy about this idea? When I say this is linear in H. And that's why even when you start talking about 2 by 2 matrices, it becomes somewhat cumbersome at some point if you're stuck with thinking of linear transformations as left multiplication by matrices. Okay? You can do it, okay? You can do it, just like we did in method 1. But the problem there is that it has a cost, first of all, to transform this function into sort of like this vectorized version. And we saw yesterday, if I think of this function, this is such a nice looking function and it makes sense to me. You know, it makes more sense. It's like take a matrix, square it. Okay. But when we vectorize everything, now it might well be like a random function. There is formulas, polynomials, blah, 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 but it doesn't really make sense to me at least. So there are situations where it's better to think of the functions the way they are given instead of vectorizing. And so how do you connect method 1 and 2? Well, the point is to figure out how to formalize the notion of vectorization. In fact, we did this in week 1. Remember that there was these functions, m sub beta. So beta is going to be the standard basis for this. So these are just 2 by 2 matrices with one in exactly one entry. And so this is the standard basis for this space. And m sub beta was this function that takes a 2 by 2 matrix and transforms it into a 4 by 1 matrix in precisely the way we did. Okay? M sub beta, right, this was the matrix representation of your vector relative to this basis goes from this space to the space of 4×1 matrices. And how does it do so? It takes a 2×2 matrix, looks at its unique linear combination. So any matrix here can be written as a unique linear combination of these. And so if I have A, B, C, D, of course, the coefficient of this is A, coefficient of this is B, C, and D, then takes these coefficients and lists them down. Right? That's this matrix representation business. Okay. If you don't remember this, you can go back to week 1. This is literally what I wrote. I mean, maybe for a more complicated space, but in this specific case, this is what this does. And then we showed, in fact, in class that this is a linear isomorphism. It's a linear transformation. This itself is a linear transformation. Taking this matrix, vectorizing it to this matrix is a linear transformation. Vectorization is linear, okay? It's invertible because if I have a tuple like this, I can turn it back into this. But then, by the fundamental theorem of finite dimensional norm spaces, we know that the moment you have an invertible linear transformation, that is to say, the moment you have a linear isomorphism, that isomorphism is immediately, automatically a diffeomorphism. So this has no cost for the purposes of calculus. In fact, it's a C infinity diffeomorphism. It's a real analytic diffeomorphism, if you want. And so, before I continue, are we happy with this? This is a diffeomorphism. So I can differentiate this. Okay, it has a derivative. So, and furthermore, actually, well, I'll say this in a second. Linear diffeo. Let me put it that way. Not all diffeomorphisms are linear, but this one is. Is a linear okay. So this is the vectorization procedure. Okay. And so what did we do yesterday? We had this function f that takes a 2×2 matrix and gives you back another 2×2 matrix. And then how did we come up with this f tilde, the vectorized version of f? Well, we just took the input, vectorized it, took the same input, computed its square, and then vectorized it again. Okay? So really, this diagram is satisfied. We defined f tilde so that this holds. Okay? Now what does this mean? This means that m sub beta composed with f is equal to f tilde composed with m sub beta. Okay? So if you remember from linear algebra, we had this similarity relation. We would conjugate a matrix by some other matrix. We would put P inverse on one side and the other side, turn it into something else. If your matrix were sort of symmetric, for instance, then you would sort of use an orthogonal matrix to do this to get a diagonal matrix, stuff like this. This is essentially the same idea, but in a nonlinear situation. And so this is the same thing as this. Cool. Okay. Well, m beta is a linear, it's an invertible map, which means that I can take this to the other side. Like so. Okay. this and this, these are both differentiable. We assumed that f tilde or f were differentiable also. And indeed, let me also mention, method 2 simultaneously computes the derivative and verifies that this function is differentiable. Method 1 doesn't do that. With method 1, we had to assume that the function is differentiable to compute the partials, put the partials in a matrix, and then deduce that that matrix of partials is a derivative. Okay? Method 2, the more sort of highbrow method, computes a derivative and simultaneously verifies that something is differentiable. Okay? So for many purposes, method 2 is a lot more convenient. There are certain situations where method 1 is more convenient also. But in any event, this says that, for instance, f is differentiable if and only if f tilde is differentiable and so on. But assuming that at least this is differentiable, I can apply the chain rule then to really relate f prime to f tilde prime. Okay. Say I'm trying to compute this. How do I compute this? I'm going to replace, instead of f, this composition. By the chain rule, I can distribute. We'll continue here. This is equal to derivative of this evaluated at this times derivative of this evaluated at this, and then derivative of this. Okay. Times derivative of this evaluated at this, times derivative of this at this. I'm just applying the chain rule multiple times. Are we happy with this so far? No, but yeah.
Should those f's have tildes?
Thank you. Thank you. OK. So remember, we had computed this yesterday. And what is this? This is the vectorized version of x. So this was the xyzt. So this is the derivative of f tilde at xyzt. OK. Now the final stage is to realize, or remember, another exercise I gave you, namely that a diffeomorphism is linear if and only if its derivative is equal to itself. This is just like in the single variable case. That is to say, for instance, this is nothing but m sub beta. It's going to be independent of x. And this is nothing but m sub beta inverse. Again, it's going to be independent of this junk in here. Okay. And we had computed this middle part. That was that 4x4 matrix of partials. From yesterday. And so what does it say then? It says that to compute this expression, f prime of x at a vector, at an infinitesimal point, infinitesimal matrix H, take the infinitesimal, vectorize it. So now it's 4 by 1. Apply this 4 by 4 matrix. This is again 4 by 1. Then devectorize it. So now it's a 2 by 2. Okay. Now, the exercise, you see this is an exercise, is to actually do this explicitly using this matrix that we computed, take an infinitesimal matrix H, say H has entries P, Q, R, S. Compute this, okay, in the 2 by 2 case. And also compute this and verify that this matches with this product. Do this explicitly. Okay. So the exercise, triangle is the same as this triangle. So this is the cost of using this formalism, okay? Somehow it gets harder and harder to keep track of what is happening. And so you need to do certain, perhaps simpler calculations. I'm not saying do this for n by n, even 3 by 3. It's going to be a lot more painful. But at least for 2 by 2, you should compute it explicitly and verify that indeed this expression matches with that expression. Then you're going to start believing that this works. Okay? Otherwise, it's going to be just some abstract stuff. Any questions? Okay. Another exercise I would like to give. This is a nice exercise, and I was hoping that I could perhaps do it in class, but I want to go on. I want to move on. Very nice exercise is to compute the derivative of determinants. Okay. So now, let's say it's from a 2 by 2 matrix, from the space of 2 by 2 matrices to reals. So it's a scalar function. What is a derivative? It turns out that the derivative of determinant at a matrix X is the linear transformation that takes a matrix and gives you back, OK, let's write it like this, trace of the so-called adjugate matrix of X multiplied by H. And this adjugate matrix is the matrix you compute when you're doing Cramer's rule in linear algebra. You look at the minor matrices, compute their determinants, put them in the right positions, and then you do things like that, and that gives you the adjugate. There's a much easier way to describe this, but I'll just leave it to you, OK? You can compute it, of course. You can expand, determinant is AD minus BC, blah, 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 vectorize everything, compute partials. It's going to work, but there's a slicker way of doing this. So maybe if you have time, we can discuss it later in class. But that's a very nice exercise. Say, at least for 2 by 2. For 2 by 2 matrices. This you can explicitly do using just definitions and so on. OK. That's all I wanted to say. So now a couple of definitions. So we're back to our regular definition, proof, theorem, claim, all that stuff. At least for a while. I think when we switch over to Taylor 2, I would like to do some, at least one example explicitly. Let's first talk about the notation lowercase d, f. Okay? So far, we have for f a function between these two open sets in arbitrary norm spaces. We took a point in X, in M, and we looked at f prime of X. Another notation for this was capital D f at X. Okay. And what is the type of this? This is a bounded linear from the vector space of the first to the vector space of the second. This is the derivative or total derivative, or Frechet derivative, whatever. We're just calling it derivative. At a point. If you don't fix the point and think of this as a function of x, then that is a derivative of f. Okay? Not at a point, but f prime. F prime by itself. And so this f prime is a function, goes from the same open set f is defined on, and it takes values in bounded linears. And again, I could denote this by capital DF. This is the derivative. Derivative as a function. Then we had the directional derivative. We fixed a point and a vector, right? And we denoted this by capital D sub v f x. And what was this? What was its type? It was a vector in f. It's not an operator now. It is ultimately, but this is the first way to think about it. Everything can be thought of as everything else, of course, but this is the first interpretation I would suggest you have in mind. So it's a vector, okay? Directional derivative of f at x in the direction of v. Okay. Now, in principle, you could vary x and v here too, and sort of think of directional derivative of f, sort of like as a function that takes two inputs, one vector, one point. Let's not do this, okay? It is something useful and important, and maybe if you have time, we'll do it later. For now, let's just think of this as you fix an x and a v, and you have a vector in the output space. Okay, that's as far as we should go for now. And we had the partials, and this was in the case when E, the input vector space, was a space of tuples, and the output space was a space of tuples as well. So this is 1, this is 2, this is 3, and then so I have the partials. Partials of components. And how did we define this? These expressions, these are nothing but specialized notation of coming from the directional derivative. Nothing significantly different between this and this. If you look at directional derivatives along the standard basis vectors, which we have in these cases, then the directional derivatives of components turn out to be this. Okay? Are we happy so far? I want you to think that this is the main object. Then this is the second main object, once you start varying the base point. And then you have sort of like less well-structured objects. You should think of it that way. Okay? And we saw examples of, oh, I have a function such that each directional derivative exists, but it's not differentiable in this sense. Somehow, if this is your main understanding of the derivative in multivariable, what you learned in single variable generalizes with the least amount of effort. Pain, maybe. Maybe not effort, but pain. So once we start talking about Taylor, the expression of Taylor is going to be literally the same if we use this. We're not going to need to use like Hessians, gradients, whatever. So we have one definition for the derivative. And if you state it properly, that definition of the derivative is exactly the same as a definition of the derivative in single variable. And that is this definition, OK? Of course, in one dimensions, in single variable, all of these different derivatives turn out to be the same thing. Okay? They all collapse to the same thing because everything is a number, or can be identified as a number. So we have now things like lowercase d f. This is what is called the differential of f. And we have gradient of f. So let me put here. We want something like this, and we want something like this. So this is the Doritos f, or grad f. Okay. So we need to make sense of these things. How do these things fit into this picture? And there's a reason why I'm using the notation this way, OK? So in the textbook, you're going to see, for instance, lowercase d is used for this. But then second derivative becomes lowercase d squared f. But that d squared, OK, because of what we're going to discuss later, the Stokes theorem, it should be defined as something that is always 0. OK? This is like one of the fundamental laws of math. You want to have lowercase d squared to be 0. Somehow, in a similar fashion, in a dual fashion, this is also the reason why I didn't denote the boundary of a set with the partial, because again, I want partial squared to be 0 also. Okay. This probably doesn't make sense right now. It will eventually. So at Stony Brook, I think, Simon Center, they have this, what is called the iconic wall. I would recommend that you have a look at it, a picture of it. It's like a big sort of like wall, and like etched on it, there's a bunch of like math and physics stuff. And I think one of these is on it, OK? And there's like a whole story why this is there, that other thing is not there, and so on. But anyway, because I want lowercase d squared to be 0, I cannot be using d as this, OK? Because I should be able to talk about second derivatives also without second derivative being 0. OK, so let's try to make sense of these. First, lowercase d. A differential 0 form, okay, on M is nothing but a function on M taking real values. It's a scalar valued function on M. Let's denote it by beta. I don't want to call it f, OK? A ck differential 0 form is a ck function. K, an integer, possibly 0, so continuous form, the continuous differentiable form, and so on. Still 0 form, though, OK? On M is a ck function, eta, taking real values. And I'm going to denote by ck-4 form to the 0 of M as a space or as a set of all CK differential zero forms. So we have two indices, OK? This 0, for now, we only have 0. There's going to be 1, 2, 3. It's going to go on. We have k, 0, 1, 2, 3. Maybe infinity, if you want. This is somewhat idiosyncratic. Typically, people write maybe capital omega. Sometimes they write lambda. Maybe there's like more complicated notations. Because I get confused, I just write it explicitly, OK? I would suggest you do that too. Now, it turns out that df, then, is better thought of as what is called the differential one form. And it's nothing but the derivative of f, OK? So I'm going to define lowercase d of f to be the same thing as this in this special case when the output space is R, OK? For eta in, let's say, CK, 0 forms, k at least 1, so that I can differentiate. D eta, okay, let me say it like this. The differential, or I'm also going to call it exterior derivative. Okay. D eta is, by definition, well, I told you that I'm just going to define it as a derivative. So it's going to be just eta prime. Okay. And just like in this case, I'm going to say that this eta, rather, this d eta is a ck minus 1, because I used one derivative, differential, now one form. If you take a 0 form, differentiate it, now you get a 1 form. So this is a preview for the third part of the class. Let's not worry about the regularity. I want to think of this d eta as a differential one form. In the third part of the class, we're going to define what it means for something to be a differential one form. But right from the get-go, I'm telling you that d eta is going to be a differential one form. Not all differential one forms are going to be of this form. Those that are going to be called exact. Okay? This should remind you of things like exact differential equations. So are exact. Let me say it like this: are of this form. Are of the form. Those that are called exact. exact. Exact differential form. Now, there's also something called the vector field. And differential forms and vector fields are somewhat related. But for now, let me just say that exact differential one forms are analogous, let's say, to what in Calc 3, for instance, you called a conservative vector field. Okay? And then whenever you had a conservative vector field, okay, this was called a conservative. Imagine you get to call this a conservative vector field. Well, you would compute this eta, and you would call this eta the potential. Okay? So we're just like replacing all of these pieces. For any exact omega one form, an eta such that d eta equals omega is a potential. How many different potentials can there be for an exact? Well, we should just think any two potentials should differ only by a constant, just like potential energy. Right? It depends on your coordinate system in physics. We'll get there later. Okay? This is just a preview. I don't know, in a month, we're going to switch over to this differential formalism, because somehow it turns out that in multivariable calculus, if you rephrase everything in terms of differential forms, that sort of simplifies a lot of fundamental theorem of calculus statements. Green's theorem, divergence theorem, Stokes' theorem, they're all going to be just integrals of differential forms. Okay? We're going to spend a lot of time on this. Okay. So that's that. So the short of this for now is that lowercase d, as opposed to how it is used in the textbook, is something specific for me. It's something that I use in the realm of differential forms. Okay? And that's why I'm not using it when just looking at derivatives and stuff. Okay. So now let's define a vector field and then the so-called gradient. Vector field, and you should think of a vector field as essentially a first-order ordinary differential equation. Okay? On M is, well, what do I need to do? To each point, to each position in M, I need to associate a vector. Is a function from M to E. Okay, so for instance, in my open set M, if I have a path that is differentiable, let's imagine its derivative. Its derivative should be a vector, and a nice way to think about it is that at the point gamma of t, there's a gamma prime of t that is supposed to be a vector. And I want to think of that vector as a velocity, which means that I want to tether that vector to this point. And so this is a special case of a vector field. You see, at each M, at each point in your path, you associate a vector field. And likewise, I can define continuous vector field, C1 vector field, whatever. If a vector field is nothing but a certain type of function, CK vector field is the same thing as, vector fields is the same thing as the space of all CK functions from M to E. Okay. Any questions so far? I know this is somewhat abstract. I'm just defining a bunch of things. It's so that in your subconscious, these sort of like blossom. In a month, it's going to be useful. So just try to keep an open mind. Try to sort of connect what you already know with some of these definitions. And so now we need to define this gradient, okay? As opposed to the differential, okay, as opposed to df, lowercase df, it's a differential form. Gradient is a vector field. And so how do I define this? In fact, now I need an inner product. So far in differential calculus, we weren't using any inner products. Everything was in the world of normed spaces. For the gradients, I need an inner product. If E, the input vector space, is an inner product space, so not only do I have a magnitude, but in fact I can talk about angles now, but I need a certain property such that the inner product satisfies the following property. Well, this property is going to be something that essentially allows me to talk about adjoints in the sense that you worked on in one of the previous problem sets. Well, the function that goes from E to the space of bounded linears on E, taking real values, where you take a V vector, send it to inner producting with V. Okay, if I fix one of the vectors in this inner product, I know that by hypothesis, this is one of the axioms of an inner product, in this entry, this is a linear transformation. And it's a bounded linear transformation by Cauchy-Schwarz-Bunyakovsky inequality. I want this map to be a linear homeomorphism. So I want it to be a bounded linear transformation. This transformation itself, the thing that goes from here to there, I want this to go from here to there in a bounded linear fashion, and I want it to have a bounded linear inverse. With bounded linear inverse, so this is what is called the duality property. I'll say more about this. If my inner product satisfies this axiom, this hypothesis, then I get to define the gradients for any zero form. Comma. Then for any f C1, taking real values, grad of f, which is the same thing as Doritos of f, is the vector field is the vector field defined by well, for any x in M and for any v in E, grad of f at x, now it's a vector, inner product against v is df. At x applied to v. It's a mouthful, but for now, you don't need to understand why all of this is happening. Just know that grad of f is going to be a column matrix. df is going to be a row matrix. Okay? This is the thing you need to know. Okay? It's going to be of this form. For matrix algebra to work underneath all this, you have to do it this way. Okay. I know this was a lot. Don't worry if this is confusing. It was meant to be confusing. In a month, it's going to make a lot more sense. Okay? Because we're going to really sort of study all of this. I think it's a good place to stop for now. Thank you. I'll see you on Friday. We're going to do mean value theorem. OK, let's start. Good morning. Not too many people today, as expected. This is one of the fundamental laws of undergraduate education. You're not supposed to leave important topics for the class before a break, but that's what happened this time. So part of me wants to perhaps postpone mean value theorem, but we're kind of behind, and I don't think I can afford that. So we are going to continue with one of the most important things, mean value theorem, in this class. Before that, though, I wanted to say a couple more words about this gradient, because the definition of it is somewhat sort of, you define it in a roundabout way, and there's reason for that. In the abstract setting, we have this, so to speak, duality property. And I want to say a couple more words about this duality property, but maybe I'll just talk about gradient in the case of tuples, switch over to mean value theorem, cover that, and if you have time, we can talk about gradient, or this duality property, and perhaps different geometries. Just a little bit. Just to recap, now I'm looking at the situation. Okay, I have a function, real valued, as usual, defined on an open set of some norm space. But in this case, I'm looking at the situation where the norm space, the normed input space is Rn. And so if I fix a point in M, by definition, it's going to be a tuple of numbers, of course. So you can write it as x1, x2, dot, 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 xn. And how did we define the differential of f at x, or in other words, exterior derivative of f at x? This was a lowercase d. Well, this was nothing but we defined this to be the uppercase df. In other words, f prime. And what was the dimensional analysis? Well, this was supposed to be a linear transformation from this space to this space. So if it's supposed to be from Rn to R, well, it's going to be a 1 by n matrix. So it's going to be a row matrix. And what are the entries? Certainly, it's nothing but the partials. So you have n partials here. You put each of these partials in one of the entries. Okay. And how do I think of this as a linear transformation? Well, I say if I were to take any vector v in E, right, it's another tuple of numbers. But we said that tuples we should think of as column matrices, and transformations, at least in the conventional sense, are supposed to act as lift multiplication. And so if I were to take a vector, again it's a tuple, Rn, what is df of x supposed to do on B? Well, you just take this and write it next to this, and you dot product. So I have here a row matrix, or if you want, it's a transpose of a column matrix. And then I think of this as a column matrix by itself. Right? Now I get to do this matrix multiplication. And based on dimensional analysis, this is 1 by n, and this is n by 1, which means the product is going to be 1 by 1. Right? It's just going to be the sum of the corresponding products. I from 1 to n, ith partial of f evaluated at the point x multiplied by the ith component. Okay. So this is how you would write things down in terms of components. But remember, even in week 1 or 2, we had this issue. Once you sort of like open up linear algebra, it turns into a bunch of summations of numbers, and then you have to do some sort of index management. And the point of everything that we've been doing was to sort of, instead of writing things in this form, to sort of use matrix algebra, which required us to be a little bit more careful with the types of the objects that we were dealing with. But that was sort of the benefit. It was a trade-off. Either you're going to use indices, or you're going to have to be careful with the dimensions of the matrices and stuff. Are we happy so far? OK. So I want to relate this to the gradient. There was this important property that this inner product is supposed to satisfy. But let me just say for now that in finite dimensions, for any finite dimensional normed vector space, or for any finite dimensional inner product space, that star property that is required to define the gradient is satisfied. In particular, in this case, it is satisfied also. So grad of f at x is a vector. Okay, it's a tuple of numbers. Let's try to figure out its entries. Let's call them for now alpha 1, alpha 2, alpha n. Now, this is defined so that for an arbitrary vector v, df of x applied to v is the same thing as grad of f at x is inner producted with v. Okay, is defined. So that for any v, any tuple, we have that df of x acting on v. Let me write it like this. Is the same thing as grad of f at x against v. Well, what is this right-hand side? In this case, this inner product, in the Euclidean case, in the case of tuples, is the standard dot product. So this is nothing but the sum of alpha I v I. And we just computed on that board that this is nothing but partial of f, the ith partial of f vi, sum of all of these terms. Okay, so this equality, so this number has to match with this number. So alpha i's, each of these numbers, has to be defined in such a way that this is equal to this for any v. Now, here's the question. From this, I hope you can expect, it's reasonable for you to expect that alpha I should be the ith partial. Right. But how do I get that? How do I justify that if this is equal to this, then in fact, alpha I is the ith partial of f at x. Just from this being equal to this. Say again?
Can you just look at the two summations?
Okay.
And it's obvious.
Well, this is a number and this is also a number. How do I single out one of the summations, one of the terms? Just because a plus b equals c plus d, you cannot deduce that a is equal to c, right? So there is something there. You're right, of course, it is obvious, but part of this class is to be able to justify why obvious things work the way they do, right? How do I go from here to there? Of course, I'm tricking you. This is not just one equation, right? It says for any tuple. So there is nothing stopping me from choosing standard bases. I can choose v to be 1, 0, 0, 0, 0, right? If I were to choose 1, 0, 0, 0, this sum would be nothing but the first partial, and this would be nothing but alpha 1. Do we see this? And then I would switch over to the second standard basis, 0, 1, 0, 0, and then this would turn into the second partial of f, and this would turn into alpha 2, and so on. So this is how you would argue that indeed grad of f at x is pretty much the same thing, you see, as df of x, except that because grad of f is a tuple, okay, it's a column matrix. That's the only difference. And so in the textbook, you're going to see gradient is defined to be the same thing as a differential, because Taylor only, so our author, works mostly in this situation, and for most things, it's not very important, because ultimately, however you define it, ultimately you're going to act on vectors, and it's going to turn into the same sum of numbers. But if you want to sort of use the full power of matrix algebra, you have to be careful with row matrices and column matrices. So there's a difference between this and this. Namely, one of them is the transpose of the other one. Right? If transpose didn't matter, we wouldn't have spent so much time in 2270. So it does matter. OK? And so this important property, this hypothesis in the definition of the gradient, is so that you can pretty much do the same thing in an abstract situation also. That's all there is to it. So ultimately, you should think of grad as the transpose of df, even in more abstract situations. Are we happy with this? OK. later on, we're going to talk a little bit about how to visualize vectors. So this is a vector field, as opposed to forms. So this is a form, that's a vector field. So this is vectors or vector fields, column matrices are more like velocities, whereas row vectors are more like momentum. Okay? And so if this tells you something about speed, this tells you something, this is something like a speedometer, if you want. This is something that detects how much you go, or how fast you go in a certain direction. Okay. See, because calculus is the way it is to simplify certain ideas in physics. Even though I don't know much about physics, I know just enough. Let's put it that way. Maybe not enough, but enough for this class. Mean value theorem. Now, before I start talking about the mean value theorem in multivariable calculus, I want to say one thing, which is that the format you're used to in the context of single variable calculus, of mean value theorem, it's somewhat misleading. Okay? In 1D. Now, what does it say? Let's state it this way, just to be compatible with our notation. If I have, let's say, an open interval, okay, let's call it I, and a continuously differentiable function on it. Again, I don't need continuously differentiable, but it just makes things easier to state. An open interval and f be a C1 function, continuously differentiable function. Then, well, for any, let's say, lambda n row in I, lambda to the left of row, so lambda left, row right, with lambda to the left of row, what does it say? It says that there's a point, there's a midpoint, let's call it mu, where the rise over run is exactly f prime of mu. F of rho minus f of lambda equals f prime of mu times rho minus lambda. Okay. Do we remember this statement from 30 to 10? And then there's sort of like a more souped up version of this, which is the Cauchy mean value theorem. It uses two functions. Let's not get into that. It's not super important. What is misleading here is that this format is, it tells you more than, or let me put it this way. It looks like it tells you a lot by telling you, oh, there is a mu where you have equality. In principle, when you think about it, mean value theorem says almost nothing about what this mu is, where it is. It just says it's some point in between. It doesn't tell you it's a unique one. It doesn't tell you any estimates. Okay, so this is a soft statement. And so really, you have no control over this mu, other than the fact that it's between lambda and rho. So let me draw the picture as well. This was my interval, let's say, and then let's say this is lambda to rho. This was my original interval. And then I looked at f of lambda and f of rho. And it goes like this. And then you look at this I guess you call it the secant line. And then mean value theorem says, oh, there's at least one point where the slope is the same. But there could be multiple, whatever. And when you really think about it, the proof of this, the way we did it last semester when I was teaching this, we first proved what is called the roll lemma, which is a special case of this. You assume that f of lambda is the same thing as f of rho, and they are both 0. And then you show that there is a midpoint where your derivative is 0. Okay. And how do you show that? Well, when you think about it, you're actually using the fact that your graph, so the graph of the function, it can only go up or down when you're going from left to right. So you have only so much space to go. That's ultimately what you're using. So in higher dimensions, this is not the format that we're going to use. And in fact, in most situations too, even in 1 dimensions, you're not using an equality, but you're using rather something slightly weaker. Namely that you use the fact that this is bounded from above by this length times, well, an upper bound of f prime. So some norm of f prime. Maybe you take something like this, imagine. Soup, where mu varies between lambda and rho, of f prime of mu in absolute value times rho minus lambda. You use something like this. Why? Because even though certainly this is useful, often having the necessity to use this specific point ends up becoming more than what it's worth. And you see, this is a lot more nicer to control. It's a lot nicer of a number, if you want. Just depends on f and lambda and rho, really, but let's not worry about that. So really, when we come to multivariable 2, something of this form is what we're going to shoot for. And we're going to do this in 2 steps. First, I'm going to show a mean value theorem for paths in norm spaces. Then we're going to generalize to arbitrary functions. Mean value theorem for paths, let's say, or mean value theorem 1. How do I want to state this? Let's see. OK. So the standing assumption is that I have an open subset M in E and another open subset N in F. I'm just going to use M in E. And I'm going to say this. Let I be an open interval. And let's let gamma to be a C1 function from I to M. So it's a continuously differentiable path in M. I'm going to draw a picture in a second. Let me just finish the statement. Then the mean value theorem says the following. For any lambda and rho in my open interval, I have the following. Then for any lambda and rho in I, such that lambda is to the left of rho, we have that the distance between lambda, or gamma of lambda and gamma of rho, is bounded by something. This is a distance between the 2 points in the path in my set M. This is bounded by sup of gamma prime t, or maybe let me write it like this. Let's say t varies between 0 and 1, and then I'm looking at gamma prime at 1 minus t what am I trying to say? It's lambda plus t rho. Times lambda minus rho, absolute value. Let me think. 0, it's at lambda. At 1, it's at 1. OK, so what is happening here? First of all, this is very similar to this. And in fact, I could literally write the same thing here. Maybe it's better. Sup of gamma prime at mu, and so this should be in E, of course, where mu varies between lambda and rho. And then the same thing here. OK. So what is happening here? Let me draw a picture again. You should first note at least the formal similarity between this inequality in 1D and this inequality. Okay? These are pretty much the same idea. Not this, not the equality, but the inequality. And so here's the picture. I have here the real line. Let's say this is plus infinity. And somewhere here is this open interval I. OK. You see the endpoints are open. And from here, I have a function gamma. It takes values in this open set M. Right? So it's a blob. Let me draw it like this. And in fact, let me put here N, because that's going to work better with the second mean value theorem, I think. And this should be F now. OK. And so I have this blob N inside this normed space F. And so the image of this, let's say, I'm not going to draw the whole image, but I'm just going to look at the part of it from lambda to rho. Lambda is a point in I, and so is rho. Let's say lambda is here, rho is here. So you see lambda is to the left of rho. This is positive infinity. You're going from minus to plus infinity. And so as you're moving in your time space, you look at the image of this time under your path, under your function gamma, and it draws a path in n. Okay? So let's say that at time lambda, gamma is here. It keeps going on like this. And then here, when time is rho, you end up at this point. Okay? So I started at this point, and I moved. Maybe let me draw it much smoother. Yeah. Are we happy with this so far? This is, so mean value theorem, this inequality is one of the fundamental inequalities in differential calculus. So if you have an inner product, remember, you had the Cauchy-Schwarz-Boyakovsky. If you had a metric space, you had triangular inequality. This inequality is pretty much at the same importance, but it requires differential calculus, you see? So I want you to really understand what is happening here. Now, let me mention this. In a textbook, for instance, you're going to see a much weaker version of this in terms of the output space. But one thing I want to say is the following. Typically, what you would see is you would have a path that is defined on a closed and bounded interval that will be continuous and differentiable on the interior. That's how they would state mean value theorem. You can do it that way too. But this is somewhat nicer to state. You see, I don't need to sort of like say many things. I just assume that this function is C1, blah, blah, blah. It works. And another thing, too, is that I don't need to worry about differentiability at these endpoints. Because I know that even though I'm looking at that part of gamma of this path between these two points, in principle, by the way I defined gamma on an open interval, I have some epsilon that I can use if I want. There's an extension. And likewise here too. And so what the derivative is at this point is not a matter. There is an extension that I'm not using in this situation. Okay, that's sort of why I'm choosing first an open interval, then I'm looking at the image of a closed subinterval. Another thing too is that when it comes to differential calculus, it's better to look at open subsets. You see, we've been using always differential functions or differentiable functions on opens, between opens. So that's also one of the reasons. OK. So now, what does this inequality say? On the left-hand side, I have the distance between the two endpoints. Now, this is not the intrinsic distance, OK? This is the subspace distance, but not the intrinsic distance that we discussed in a previous problem set. And so the left-hand side here is nothing but the length of this line segment. You see, I drew this blob n in this manner so that the line segment was not fully inside n. But that's not a problem, OK? So this is the left-hand side, the length. What is the right-hand side? Well, let's first look at this. Certainly, lambda minus rho is just a number. It's just the length of the input, right? It's this length. How about this soup? Well, in this soup, mu, the midpoint, varies between lambda and rho. At each mu, I look at the vector, which is a velocity vector, gamma prime of mu, look at its magnitude, then I take the soup of all of these. So this is, in a sense, the maximum speed of your path. Now, in this picture, you see the split, the input and output. So you don't really get to see the velocity in this. This is not the graph of gamma, okay? Because in the graph, you would have time information as well. You would have time and space together. Here, we're just seeing the space part. So you're not seeing anything about the velocity. But at the very least, we can say, well, at each point, mu, let me use a different color. This is mu. It's going to vary from here to there. And as mu varies from here to there, well, gamma of mu is going to vary from here to there, following this path. Okay, maybe let's say at mu, this is where my path is. And of course, I hope it makes sense to you to think of gamma prime of mu as the velocity vector of this path at this particular point. Let's say it's like this. Are we happy so far? Okay. Well, at each mu, at each time parameter, I have one point and one vector. We're going to look at the magnitude. If this is supposed to be velocity, its magnitude is supposed to be, by definition, it's a number. Well, it's supposed to be a speed. And so this, you see, this is precisely the max speed of gamma. Is this really max? Well, yes, because any continuously differentiable function is continuous, and this closed and bounded interval, it's compact. We know by the maximum principle, continuous functions on compact sets, they attain their max. So if I wanted, I could have used max here. Okay, so indeed, this is the maximum speed. Okay. Any questions about all this? So how do you prove this? Well, I'm going to give you two methods. One of them is based on this idea of the length of a path that you looked into in a previous problem set. The other one is sort of the more explicit calculation. Because you see, forget about norm spaces and stuff like that. We had seen how, given any continuous path, we could define the notion of its length insofar as it takes values in a metric space. And how do you do this? Well, you look at the path, you take finitely many points. Let me do this again. Look at this. Say I have here a continuous path that goes from here to there. Well, if you want to associate a number that is supposed to be a length, well, one thing you do is this, right? So you take finitely many points on this path, and then you look at pairwise distances. You add those distances up. That gives you a proxy for the length. And then you keep taking more and more data points in the limit, insofar as that limit exists. And as a finite number, you call that the length. And so how would you start that approximation? Well, the best or the worst approximation is to just look at the endpoints and look at the distance. Okay? Now, in an abstract metric space, you may not have available this line segment. But in a sense, there's a virtual line segment, which is the distance precisely between the endpoints. Okay? And then what you would do is, what I was saying, is that you would take one more point, let's say. And then you look at this virtual path. So you increase the length, you see? And then you would take more and more points. Does this make sense? You worked on this in a previous problem set. But I guess what I'm trying to say is that somehow this left-hand side is a very crude approximation for the length of gamma. Well, I'm going to leave it to you that if in your metric space, so if your metric space is a subset of a norm space, then indeed the length of the path is the integral of the speed, as you're familiar with. Hang on. I'm going to write it properly. Let me write it there. Length of gamma defined in this way, defined in the way that we defined in a previous problem set, is the integral of its speed. It's a very nice exercise. It's so nice that I might even put it in the second midterm. Okay. Now, does this make sense? Well, note that even though gamma takes values in this possibly abstract norm space, I'm going to take its derivative, so it's a vector now, then I'm going to take its norm. So what you're integrating is a real valued function on an interval. So this expression is completely within the realm of 3210. So you know what this integral means. Okay? Is this integrable? Well, yes, because gamma is continuously differentiable, which means that gamma prime is continuous. And we know that linear algebra is continuous. In particular, norms are continuous. So this, the integrand, is a continuous function of t. Continuous functions are integrable, Riemann integrable, and any other type of integrable too, but Riemann integrable at the very least. And because of this, this makes perfect sense. This is a very nice exercise. Take this definition of the length and show that it's indeed equal to this. But then if you have this, I hope it is immediate that mean value theorem 1 has to be satisfied. Okay? Because by definition, this, the left-hand side, is dominated by the length. And then this is equal to this, but then the integrand is dominated by this soup. Okay, let's prove it like this. That's the first proof. It uses this exercise. So first proof. Proof of mean value theorem 1. Well, this left-hand side is by definition dominated by the length of gamma. Which by the exercise is the same thing as the integral of the speed. And we know that if I were to take the integrand in an integral and grow it by some other thing, then the integrals are going to grow. That is to say, integration is a monotonous operation. Soup, or max, let's say, doesn't matter. But then this is a number. It doesn't depend on t, which means that I can take it outside the integral, and this integral is nothing but the right-hand side. And rho minus lambda. Okay. And so if you have this formula, that the length of a path insofar as it is differentiable, let's say continuously differentiable, is the same thing as the integral of its speed. If you have that formula, then this is almost by definition. Okay, you just use basic properties of the integrals and so on. Are we happy with this? Now, the second proof doesn't use this. We're going to have to use sort of the C1 property or differentiability property of gamma. 5 minutes probably it's not going to be enough, but let's think about it. Now we're going to have to open up the definitions and use epsilons and deltas. And I'm going to tell you exactly where you can stop the proof I'm going to write and transform it into a proof of this exercise. And by length of gamma, of course, I mean the length of gamma restricted to lambda rho. Okay. Proof 2. We know that gamma is differentiable at any time t. So let's open that up, see what that means. Instead of using this little o business, I'm just going to use epsilon deltas because I really want a little bit more control. For any t in lambda rho, gamma is differentiable at t. That is, well, for any epsilon, there's a delta, all that stuff, okay? For any epsilon, there's a delta, such that for any h, okay? And in fact, yeah, let's leave it like this. For any h such that h is bounded by delta, what do I have? I have that gamma of t plus h minus gamma of t plus gamma prime of t times h in norm divided by h in norm. And in this case, h is a number, so this is just a this is a number also. Nothing too complicated. So this is bounded by epsilon. Okay. Well, what I can do here is that I can use the fact that gamma is a path, that is to say its input space is one-dimensional. In this case, I can take this scalar, distribute in this numerator, and get rid of this h. And in fact, I'm going to distribute this minus as well and write it like so. Minus gamma prime of t. Okay. So this is the same thing as this. I'm saying, well, by the differentiability of gamma, this is bounded by epsilon. So the point is, I want to think of this close to this. And if these were real valued functions, this would be very easy. I would just say, get rid of these absolute values and put a minus epsilon here. But of course, in this case, this doesn't make sense because these are numbers, these are vectors. It doesn't make sense to bound differences of vectors by numbers. So I need to do something else, slightly different. You don't get to do this in multivariable. But what I do have is, remember, something called reverse triangular inequality, which allows me to basically put norms between on this and on this part, and that would decrease this bound. So this is lower bounded by and just to be clear, this is in F. this is in f minus norm of this. Then this is the absolute value. We're almost done. Now you see I have the difference of two numbers. I'm saying that that difference is bounded by epsilon. Then I can put minus epsilon to the other side and so on. Open up this absolute value. And so if you continue from here, that's going to lead to the to a proof. That's going to lead to a proof of this exercise. We're going to instead use the bound that we have, the sup, max speed that we have, and that's going to lead to the proof of mean value theorem. Okay, the proof is not done. We're going to continue working on it when we come back. Okay, have a nice holiday, and I'll see you, I guess, in a week.